Okay, thanks a lot. So what I'm going to talk about is from a joint paper with Jim Conant, Martin Kasabov, and Karen Vogelman. So the basic problem is to see what can be said about the homology of the automorphism group of a free group. So Fn is going to be free of rank n, the free group of rank n. And then it has an automorphism group and an outer automorphism group, a quotient by inner automorphisms. And the problem is compute the homology of these groups. And this is all going to be rational coefficients throughout the talk. And I'm not going to write the coefficients after this time. So let me start. Well, why would one be interested in computing these things? One is because of the well-known analogy of automorphism groups of free groups with mapping class groups of surfaces, and also SLNZ. So if you can make some progress in one of these three cases, you might be able to apply the ideas to the other cases. And the other two cases are more classical than this case. But more concretely here, well, suppose you're looking at, well, go back to the mapping class group of surfaces. So cohomology there gives you characteristic classes for surface bundles, smooth surface bundles. And so the analog here is cohomology for, well, homology or cohomology, not much difference. So cohomology would give you, for ought or out, would give you characteristic classes for fibrations, where the fibers, well, there are two possibilities. The fibers could either be actual finite graphs of rank some number n, fibrations with finite graphs as fibers, or turns out to be equivalent, just fibrations where the fibers are homotopy equivalent to graphs of rank n. So that's another motivation for being interested in this cohomology. So let me start by summarizing what's known. Again, I'm going to leave out the Q coefficients, but always they'll be implicit. So, well, the very first thing, I suppose, is that these groups are finally generated. Well, they're vector spaces over Q, so that means finite dimensional vector spaces over Q. That's even true with integer coefficients. Finally generated, and 0 for n bigger than the virtual cohomological dimension, which is 2n minus 2 for ought and 2n minus 3 for out, Fn. So this goes back to Culler and Vogelman, their original construction of outer space. So that's one fact. So over here, I have a little chart to indicate, as I go along through what's known, this chart indicates some of that. So there's this line of slope 1/2. So here's, horizontally is the I direction for the ith homology, and vertically is n for the rank. So this area over here is above, I is bigger than the DCD. So there's that region where everything is 0 for dimension reasons. Next thing is stability. So that HI is independent of n for once n is big enough, namely something that's known to work 5/4 I plus 1. So slope 5/4. That's this line here. So here, if you go vertically far enough up, the groups you get are independent of n. Stability is known, even with integer coefficients, although with integer coefficients, the known range is not quite that strong. Then the stable homology, rationally, is actually 0. That's the big theorem of Soren-Kalasius a few years ago. So I put the 0 up here. So this is in contrast to those other cases that I mentioned of SLN, Z, and mapping class groups of surfaces. There is some non-trivial stable rational homology. Here there is not. So anyhow, that means there's just this wedge between slope 1/2 and 5/4 where you could get non-zero rational homology. Another fact that's known is, well, there are the two cases, ought and out. If you go from, there's a natural map from ought Fn to out Fn, rational coefficients. This is surjective, always. It's in an unpublished paper of Kawazumi, I believe. And in this more recent paper, that paper was several years ago, of Kawazumi, our more recent paper gives another proof of this. So, right, so ought has at least as much homology as out, rational homology. Okay, so there have been some low-dimensional calculations using computers. But they don't go very far because it just gets too hard. So these are for small I and n. Of course, you can use stability in some cases to extend the range a bit farther. So this chart shows all the known non-zero classes. So there aren't many. So the known, the ones that come just from the computer calculations, non-zero classes. There are two families. So there are Morita classes, found first by Morita, I think, in the 1990s. Mu k, that lives in H4k of ought F2k plus 2 for k 1, 2, and so, well, they're defined, Morita defined them for all k, but the only ones, so these are the circles here, H4 of ought F4, H8, H8 of ought F6, H12 ought F8. So Morita classes, and they're non-zero in both cases, both for ought and for out. That's one family, and so the solid dots are those classes, and the empty dots are the classes that were constructed. That is, cycles were constructed, but it's not known that they're non-zero beyond the first three. What?
Are they expected to all be non-zero?
That's a good question. there's not so much evidence one way or the other, or to conjecture on. I think, well, Jim Conant, maybe Karen, I think they think so, that they're probably all non-zero. But for me, the evidence is just not very convincing, not very strong yet. So, I mean, is it like stable homotopy? Well, unstable homotopy groups of spheres, where it's just a great amount of chaos without very many repeating infinite families. I guess there are some, at least in the stable case. Or is it kind of nice? Are there nice infinite families? Yeah, that's the big question, Okay, so that's these round circles. Then the squares were found, classes constructed by Conant and Voigtman in the first, originally I believe. They're called Eisenstein classes. They have something to do with Eisenstein series and modular forms. Maybe I'll call them EK. These live in H 4K plus 3 aught F 2K plus 2, 2K plus 3 rather. Again, only the first two are known to be non-zero, this solid square and that solid square, but there are cycles constructed all along the line here. So I guess one thing to notice is that these families, I guess I should say over here, that these vanish for when you pass to out. They only are non-zero, only have a chance of being non-zero in the ought case. Yeah, so all these classes, they're close to this line, the VCD line. So they're, in fact, just 1 or 2 dimensions away from the VCD line. Nothing known about over here, much closer to the slope, the stable range. So this 5/4 might not be best possible. It might be slope 1, for example. Okay. So these are computer calculations, and well, they've been pushed about as far as they can go. I haven't been involved myself in them except in the very first one that Karen and I did. Morita also showed the first one was non-zero earlier. So let me mention something else known. So the big question is just what Benson asks. How many of these are non-zero? There's some evidence, also computer-based, from Euler characteristic calculations. One can compute Euler characteristic in a little bit wider range than you can actually do calculations. So this is Morita, Sakasai, and Suzuki a few years ago, fairly recent. So N and the Euler characteristic, this is for out Fn. So what this means is take a classifying space and compute the actual honest Euler characteristic. So it's telling you something about non-zero classes. So 1, 2, they've computed this up to 11. Let me write down the results. So they begin reasonably. There's nothing interesting happening below F4, this first class here. Then the next one is in F6, this one. So that's another 2. an even dimensional class. So there's always, the zero dimensional class that's included in here. Here, one would expect another 2 because there's this third class here in H8. Sorry, this one. However, the Euler characteristic is 1. Euler characteristic is 1. So that says in rank 8, there has to be an odd dimensional class somewhere along here as well. But then for 9, 10, 11, things start to go crazy. The numbers are much bigger and negative. Minus 21, minus 24. Let me write them down. Here it's minus 21. Here it's minus 124. Here it's minus 1202. So the numbers are negative. That says they're odd dimensional, lots of odd dimensional homology classes. And this is out. So at the moment, the known non-zero classes are just these even dimensional classes. These Eisenstein classes are only non-trivial for ought. So there aren't any known odd dimensional classes, but there are lots of them. And maybe this pattern continues, and these get bigger and bigger negative. That's what one might guess. So like in the next case, 9, up here, there's along this horizontal line, there's a lot of stuff in odd degrees. I mean, it could just all be focused in a single degree, and lots of classes that are linearly independent, but sort of all the same type. Could be that, or they could be lots of different types of classes. I don't know. Nothing known. Okay, so mostly what I'm going to talk about is these known classes, especially the Morita classes, how to construct them, what they look like. So in this paper, that's sort of the point, one of the points, to get not just for these classes, but for a general framework for describing these classes in a simpler way. So these three people have at least one or two joint papers before I got into the project, and before that, Karen and Jim had a paper without Martin earlier, and they use a lot of heavy machinery to construct these classes, these sequences of cycles that are candidates for non-zero classes. So one of the points of this recent paper of ours is to get much simpler and easier to understand and more geometric constructions. Okay. So I'll start with something that would come even before the Morita classes, some classes that turn out to be zero. So I said the VCD for aught Fn was 2n minus 2. So let's talk about abelian subgroups of aught Fn and also out Fn. So the first one, there's a Z rank 2n minus 2 that gives the VCD. So it gives the lower bound, and then there's another argument that says that's also an upper bound. So I want to describe these geometrically. So I'm going to think of homology of aught Fn geometrically. So a model for the classifying space rationally. Well, the quick way to say it would be, well, if I were doing, it's outer space, or the base-pointed version of it, mod, so outer space, color-Bogman space, the base-pointed version, modulo the action of aught Fn, if you happen to know what that is. But so what it is space of all finite graphs connected, rank n. The vertices have valence at least 3. I guess that's all I need to say. And to get out, to get the automorphism group, I want them to be base pointed. If I were doing, so base points for the ought case, with base points chosen in the ought case. So, so we allow, as you move around in this space, so these are isomorphism classes. So if two graphs are isomorphic, you consider them the same. That sort of looks like a combinatorial object, a discrete object, but so you put lengths on the edges to allow to get an actual space. So you allow trees, subtrees, to shrink to points. So that's just a rough definition of it. So here's an example. So so to realize this free-Abelian group, we can map a torus T 2n minus 2 into this space that I'm just talking about here, space of graphs. So start with a circle and attach edges that go from one point of the circle to another. So like chords, they don't have to intersect. So circle with n minus 1 edges attached at arbitrary points.
Can they be attached at the same point?
They can be, yes. So this gives you a rank n graph, and the attaching points vary over a circle. So there are n minus 1 edges, each has 2 n's, so that gives you 2n minus 2 circle coordinates. So that's the torus, like that. So, so when they collide, that's really an edge collapsing to a point. So that's permitted here. So this is a not very hard to see family of graphs. So, and if you look on pi 1, the map on fundamental groups induced by this map, it's z2n minus 2 that actually injects into aught Fn. So to get off Fn, I need a base point. So no, these are one circle with, yeah, start with the case of one circle. So, well, unfortunately, or maybe fortunately, you look at the induced map on the top dimensional homology from the torus to the B aught Fn with rational coefficients. That map is actually 0 by a symmetry argument. Okay, I don't think I need this.
Is it still open whether that group is the 0 group? The particular group? The top dimensional rational homology?
Yeah, it's open. I don't know. So let me just, it's a nice little symmetry argument. So you can switch the ends of any arc, of any edge that we've attached. Take one of these edges, switch the two ends. That gives you the same graph, of course. We're only talking about isomorphism classes of graphs. They don't have any labels on them, except the base point. So on this torus, that means two coordinates, two circle factors of the torus are interchanged. So that's orientation reversing on the torus. Induces -1 on h2n minus 2 of the torus. So it reverses the sign on the homology class of the torus, but it doesn't change the homology class after you map over to the b aught fn. So it's got to go to 0. Okay.
I have a question, but does it know if it goes to 0 with g mod 2 coefficients?
I don't know, not known to me. Right. Right, we didn't really think about integer or finite coefficients. Sounds like a reasonable question. Okay. So this is something that doesn't give you anything non-trivial. Let's try something just a little fancier, something that will give the Morita classes. So now start with two circles. Two circles and joined by an odd number of arcs or edges. So one of these edges we can just think of as fixed, sort of like a base point. I mean, after all, you can rotate the circle, so you might as well fix one of the attaching points on each circle. So 2k of them attach at arbitrary points. And in fact, if you wanted this one edge that you think of as attaching to the base point in both cases, you could even collapse that down if you wanted and get a wedge of two circles with 2k arcs, edges. Not really different, but it's maybe a little better to think of it with two separate circles. So this gives you a map of a 2k torus, because all but one of the edges can attach arbitrarily. 2k, 4k, because there are two endpoints to each edge, into b aught f, and the rank here is 2k plus 2, if you compute it out. So what about symmetry? Can we use a symmetry argument to say that this map is trivial on the top dimensional homology class? Well, what are the symmetries? You could switch the two circles so that the two endpoints of each edge are transposed. So if there are an even number of edges, that's an even transposition. So you don't kill it for that reason. And that's why I had started with 2k plus 1. If I'd had an even number of edges, one of them being fixed, then that symmetry would kill the class. Okay. So that's one symmetry. Another symmetry is just permuting these various arcs. Well, say you permute two of them, that's transposing two circle coordinates and another two circle coordinates. So you get an even transposition. So, you can't, there's no argument, no vanishing argument. as there was in the first case. Okay, so in fact, so you get we get this map, did I write down? Yeah, this one. So, so you get, in fact, this mu k, the Morita class in H 4k aught f 2k plus 2. And it's known that it survives if you go to out as well. That just means forgetting the base point. Here there is we've got a base point there.
By survives, you mean possibly survives, or?
So, yeah, right. So non-zero for k 1, 2, 3. Yeah, sorry, survives. I mean, in the known cases, right? But anyhow, it's a candidate for a class, and then the computer calculation shows it begins being non-trivial, non-zero. So, so that's a nice construction. Pretty simple, and just realized by a free-weaving group. What's the rank? 4k in aught f 2k plus 2, and you could write down exactly what that subgroup is. It's kind of similar to the one over here that gives the VCD. This one is below the VCD, the 2 dimensions below the VCD. Okay, on to the next one. So those are Eisenstein classes.
I have a question. How do you show that this is equivalent to one?
Yeah, well, you ask Jim and Karen. I mean, their construction, yeah, I mean, their construction used a lot of stuff. Who is it, Consavage? I don't know. A bunch of Lie algebra, blah, blah, blah. And anyhow, they tell me that this gives it. Actually, I mean, there's some argument in the paper, but you kind of have to know the previous stuff to understand that. Actually, I mean, the way they talk about it is circle, in the earlier stuff, circles with little leaves sticking out, and then, so it's not too different looking from this, but yeah.
Is that also for any Eisenstein classes? Like, is that, am I supposed to think like related to Eisenstein's theory, Eisenstein theory?
What?
You call these Eisenstein?
Yeah, that.
I was about to say. Okay, sorry. Okay.
Yeah.
It appears to be the English more.
Yeah. Right.
Cohomology.
Yeah. Right. It's a big machine there. So one of the goals here was, from my point of view, avoid that machine. Understand, you know, what are these homology classes, these Eisenstein classes? What are cycles? So they're not going to be just abelian subgroups. They're going to be non-abelian subgroups, but they're not too far from abelian. So yeah, this is a little harder to describe. It is a little more complicated. So here I talked about the graphs. So graphs. Here the graphs were constructed in 2 stages. Start with a pair of circles and then connect them by some arcs. Oh, incidentally, you could start with more than 2 circles and connect them by arcs. That's a generalized Morita classes. There are tons of them that are constructible as cycles, but none of them are known to be non-zero. And a lot of them are known to actually be zero by symmetry type arguments. So for the Eisenstein classes, there it was 2 stages. Here it's just a little worse, 3 stages. So you first take 2 circles, C, C prime. So 1, 2 circles, C, C prime. Second stage, you attach one edge B to one of the circles. So I'll draw it out here. That's B. So the 2 ends of it can vary around this circle arbitrarily. That would give you a 2-parameter family, but you've got rotational symmetry of the circle. So there's no harm in assuming that one end of B is at a fixed point. The other end then goes around the circle like a 1-parameter family. Okay, then the rest of the graph comes in the 3rd stage. So there are 2 edges A and another one just sticking out into space here, A prime. Then there are some edges that connect like this. So D1 up to dk and E1 up to ek. And I think that's all of the edges. So the rules are, so more edges. So A and A prime attach to B and C. So I drew it with A attaching to B and A prime attaching to C, but this end of A can move all around B and C. And similarly, this, where A prime attaches, can move all around B and C. Now, the other end of A prime doesn't attach anywhere. In the end, we just think of this as the base point. Okay, so these Eisenstein classes require a base point. I mean, they give one. They're automatically 0 in out, but not automatically 0 for ought. So that's how A, and then the DI and EI attach only to C, and at their other end C prime. Well, I guess I should have said that the other end of A attaches to C prime. So, right. Anyhow, the picture is showing it. Okay, so so these D's and E's are sort of the less interesting part. They just vary, each end of them just varies over a circle, C or C prime. So they're just going to give tori like before. But the A and A prime edges are what gives something a little non-abelian. So let me tell you what the subgroup is. So B moving across C, one gets a semi-direct product here. So F2 squared. So this B comes from the one end of B moving around C. The F2 comes from the A and A prime attaching to B and C. So like this end of A can be any point of B or C. The union of B and C is a wedge of, it's a rank 2 graph, an F2. And there are 2 of them, one for A and one for A prime. And then the D's and E's just give you a Z, is it 2K, I guess? Right. 4K. Yeah, each has 2 ends, so 4K. Anyhow, this is an ought. F, you compute it out, it's 2K plus 3. K is at least 1. You need at least one D and D edge. Okay, so this part, that's where the non-abelianness comes in, this semi-direct product and the free group there. But it's not too bad. It's a 3-dimensional group. I mean, F2 is 1-dimensional, and you have product with itself. That makes 2 dimensions, and then the Z gives you a 3rd dimension. And then over here we got 4K dimensions. So, but this is not a manifold. Not a manifold. Its dimension is 4K plus 3. So it would be nice to go a step further and get an actual manifold whose top dimensional class is giving this Eisenstein class. So let me say what that manifold is. So actually, for this group, you can easily figure out what the homology is, and its top dimensional homology in this is rank 2. There's not a single top dimensional class, and it's only one of the 2 top dimensional classes that one is interested in. So a manifold. So it's going to be a 3-dimensional manifold cross the 4K dimensional torus. So let me tell you what N3 is. These are closed orientable manifolds. N3, well, you take a surface of genus 1 with one boundary component, a punctured torus, crossed with S1, and you take 2 copies of that, and you glue them along their common boundary, which is a torus, but you do it by switching the factors, the 2 S1s. So each half is just a surface cross S1, so it's, if you want, cipher fibered. But when you glue them together, the cipher fiberings don't match because we're switching the 2 factors. So it's what's known in 3-manifold theory as a graph manifold. So it's a graph manifold that gives us a manifold of graphs. So that's what N3 is. And then the rest is just the torus part, these D's and E's wrapping around the C and C prime. So it's not too bad a manifold. So the fundamental group of this is not this subgroup, but it maps onto it. So there's a map from this manifold to B aught F, whatever it is, 2K plus 3, taking the fundamental class to that Eisenstein class that was known before. So again, that takes work to verify that it really is the same thing. So this, as I say, has the advantage of being an actual manifold. So its top dimensional homology is just rank 1, one-dimensional. But this map is not injective on pi 1. Its image is this subgroup.
I have a question. Is there the other class, is it known to be non-zero? The other image, the other?
Oh,
Or 0?
it's probably 0. It's easier to understand. I think it just comes from a torus. Yeah. Oh, so I didn't say about this, what the semi-direct product is. So, below the margin is too narrow to contain it here. It's off the edge. We're using here aught F2, well, really out. Anyhow, this matrix gives you an element of aught F2, and we use the same thing, the diagonal action here on both factors. So that's telling about which semi-direct product it is. Okay, I guess I'm probably pretty short of time. Yeah, these are called Eisenstein classes because they're connected to modular forms, cusp forms, Eisenstein series, and here's the cusp. The cusp subgroup, this subgroup of GL or SL2Z. GL2Z is the same as out F2. Anyhow, Time to stop. I was going to say more about the general pattern here. The idea is, I mean, you can see in these examples, you can sort of split these graphs into separate parts, where in one part something is going on with a circle with various leaves sticking out of it. Over here we've got a rank 2 graph with leaves sticking out of it, and there's a way of assembling homology. This is really assembling a homology class here. The torus from this side is a T2K, and over here on this half, where you just have a rank 2 graph with leaves, it's a 2K torus across this three-dimensional thing. So that's really what the paper is about, these assemblies. And I'm just giving the 1-minute version of a concrete application of something in the paper. Okay, but it's time to stop.